time algorithm to further reflect human perception of audio, which I'm not going to elaborate here. So this leads us to the selection of models. There are 3 models suitable for audio data classification on edge impulse. So namely spectrogram, MFE, which is mel frequency envelope, and MFCC, which is mel frequency cepstral coefficients. The spectrogram takes a convolutional neural network approach and analyzes the image data over time series, while the MFE and MFCC does more in mimicking human perceptions before fitting into the model, either convolutional neural networks or recurrent neural networks. MFCC takes a step forward than MFE and is expected to bring kind of more detailed information and is more suitable for speech analysis. So on the next slide is the results of the models on different tasks as introduced before under the experiment design section. All models are good at recognizing sound waves with different amplitudes or with certain frequencies within the sound wave being cut off. However, when different pitches involved, all models have seen a significant decrease in accuracy. So what may these results implicate? It has been found that amplitude changes do not influence much the classification of wave compositions. Instead, changes in pitch, so the overall frequency of the sound, can often obscure the recognition of harmonic frequencies within the sound waves. From the perspective of subtractive synthesizing, these algorithms are capable of telling the original waveforms that the sounds are made from, given enough training samples and given that the overall frequency, so the pitches, does not change much within each label. So on the other hand, from the perspective of additive synthesizing, these algorithms are expected to be quite efficient in processing more complicated sound clips, where higher complexity in harmonic wave compositions can be detected. This is because the algorithms are very effective in capturing changes in frequencies. So based on our findings before, the demo task will be developed through the approach of an additive synthesizing procedure. By successfully classifying complex sounds, for example instruments, composed with many harmonics, it may indicate that there are some regular features of different instruments regarding the composition of basic sine waves. We will start with the percussion family, where pitch variation among the same type of instrument is minimal. So why kicks and toms? Let's first listen to some of the samples of kicks and toms. The acoustic ones, I would say, is quite easy for you to tell. So the kicks and the toms. There are also electronic productions of these instruments that diverges quite far from the acoustic version. So kicks and the electronic toms. And sometimes these sounds are quite similar in electronic production. So here's an example. To use deep learning techniques to tell this apart, I selected the MFE model to prefit the data. The detailed model structure and parameters are shown on this slide, with a sampling rate set as 16 kHz, window size as 1000 milliseconds, and all these mel filter bank parameters on the left. The model takes 640 features from the data, reshape the layer into 32 columns, and then put them into 3 one-dimensional convolutional layers. After going through one flattened layer and a dropout layer, it outputs the features into 2 categories, kicks and toms. The training process takes 100 cycles at a learning rate of 0.005. And then I utilize the EON tuning tool on edge impulse to choose the best models. and found that there are probably two best choices for this task, the MFE and the spectrogram model. Actually, the spectrogram kind of outperforms the MFE model by around 4% on the test site, and it is lower in performance latency, which means more timely efficient. And what's more, as the time windows for set is 1000 milliseconds, which covers most time spans of the samples, the MFE appears to have the same sampling range as a spectrogram model, which windowed over the whole time span of individual samples. Which means there's probably no need to worry about spectrogram did not go into details as much as the MFE. And the next slide shows the performance of both models on validation and test datasets for your information. So finally, let's move on to the deployment on Arduino. As you can see, the peak RAM usage and flash usages are quite moderate, which indicates it's a relatively lightweighted model. And here below, I will show a video of how this model works on the device. So that's basically the demo task deployed on my Arduino. And some future tasks I may carry on doing will include to get more data samples and increase the types of labels, and incorporating some data augmentation methods, for example, adding background noise to improve the robustness of the model in live sampling tasks in the real world. Or maybe go to the details of the model and see if there's anything can be implemented. And maybe explore the ways to enhance the models to be able to classify sound clips over different pitches. In conclusion, it's helpful to use tools like synthesizers and deep learning models to analyze and reproduce sounds. There are also many other potential applications for deep learning in sound engineering. For example, generating entirely new sounds or to enhance existing ones. Yeah, that's pretty much all. Thanks for watching.